Hello, everyone. My name is Tim McGuire. I am the Business Development Manager for Impression Technologies Limited, based in Coventry, England, with resources in the United States. ITL is a technology transfer organization who is in the process of developing the hot form quench or HFQ technologies that we'll be talking about today. I am joined here today with Alistair Foster, who is the Director of Innovations for ITL, and also with Jared Boland. Jared is a Boeing engineer working in the Boeing Research and Technology Group in St. Louis. As an ASM International member, and on behalf of ITL employees, I want to start by thanking first the Aeromat Organization Committee, especially Lindy Good and Kathy Murray. In the process overview shown here, HFQ is used to form high-strength sheet metal aluminum components where the hot forming is done with in-tool quenching. The process starts by utilizing a pre-engineered aluminum coupon where the shape, the thickness, and the aluminum material properties have been taken into consideration. The coupon is moved into an oven and heated to the solutionizing temperature. Once the solutionizing temperature has been reached, the coupon is placed in the press, where it is stamped and quenched in a one-stroke operation. The formed part is then taken out of the press and cleaned and prepared for additional operations as needed, such as trimming or aging. By taking the aluminum to its solutionizing temperature, all pre-existing stresses are relieved, and the then hot aluminum can be formed into complex shapes. The quench then stabilizes the aluminum in the desired shape before removing it from the tool. So now let me turn the presentation over to Jared Boland from Boeing to share with us his comments about Boeing's experience with the HFQ process related to a project he had to reduce cost by forming close to net shape with reduced post-forming machining. Jared?
Thanks, Tim. As mentioned, I'm an engineer with Boeing Research and Technology located in St. Louis, Missouri, supporting metallic fabrication. My introduction to impression technologies and the hot form quench processes for high-strength aluminum alloys started while researching the automotive space of high-rate manufacturing solutions. Some of the needs identified were in support of efforts to identify new high-rate manufacturing solutions for small air vehicles such as electric vertical and takeoff landing platforms. For aerospace applications, cost and weight are always important. However, we were already at a significant weight challenge with eVTOL due to the added mass of electric motors and batteries. Baseline composite structure did meet some of these weight challenges, but posed technology gaps to meet high-rate manufacturing needs at affordable cost. Two projects were initiated with impression technologies, including stiffened skins from thin sheet and preforming of structural frames for later machining from thicker sheet. The stiffened skin concept would be similar to a typical automotive hood with a smooth outer skin and a corrugated or hat stiffened inner sheet, in which the forming trials were actually focused on. The buckling loads were the primary drivers of thickness, so we were shooting for a high modulus material that also had high formability, not exactly strength. For these reasons, 6061 was selected for further trials at 20 thousandths thickness. Pictured are results of other manufacturing trade studies for a full side skin, including weight and expected cost in a high rate manufacturing environment. The chart shows increasing cost on the x-axis, increasing weight on the y-axis, and we can see the hot form quench concept is much lighter than a more conventional sheet metal skin. It does add some weight versus composite structure with the benefit of being much lower cost. Later, Ali will discuss the stage development of the application from subscale stiffening feature coupons, how they influence the final design, and also efforts on forming a subscale skin bay. The structural frame concept includes some interesting challenges, such as a one-piece design and also tight inside corner radii to maximize the cargo area of the vehicle. The intent with this concept was forming of a thicker sheet of approximately 160 thousandths or 4 millimeter, and that would later serve as a preform to be machined to detailed thickness for weight reduction. The cost and weight trade study again showed a significant weight reduction of a machine preform versus a conventionally formed frame. And when comparing to a traditional machine hog out or machine from thick plate, there was a significant cost reduction possible due to reduced machining time and also reduced raw material cost. To summarize, some of the potential benefits of hot form quenching for the aerospace industry include the possibility to increase complexity and formability and quality of sheet metal parts, the ability to make low bite-to-flight preforms versus machining from a hog out from thick plate, the capability to form high-strength aluminum alloys such as 7075, 6061, and 2024, and lastly, the technologies easily scaled to high-rate manufacturing with forming times of less than a minute. So to conclude, I'll hand off to Ali to discuss the hot form quench development for the skin and the frame applications.
Boeing came to us with a requirement to form 20 thou material. It's about 0.5 millimeter. We'd never done that before, so we started by putting together a small project aimed at confirming that firstly it was possible to form such a thin sheet, and secondly that our simulation models could actually predict what would happen. The design was iterated that took geometry aspects from the Boeing conceptual sketch and recreated them as a small prove-out pressing. We ran simulation of 3 alloys, 2024, 6061 and 7075. The simulation predicted we should be able to form the 6061 alloy very easily. We were right on the border for feasibility of the 7075 and actually above what we predicted would be possible for 2024. So I'll show you the lab setup in the next slide. We can see on this slide that the parts were successfully formed. We had success in 7075 and also in 6061, but were unable to form the geometry in 2024, which is as the simulation predicted. So this is the lab setup we use to prove out small tool sets. These provide a great way to create scaled representations of particularly challenging features for new customers being introduced to the technology. In the video, you see a hot blank at approximately 500 degrees centigrade, or just over 900 degrees Fahrenheit, being removed from the solutionizing oven. It's been transported to the tool, and then the tool presses the part and holds closed for the quench. By forming the demonstrator, we were able to validate that RFE models could be used with its thin material. We then went back to the conceptual simplified structure and worked to convert that into something which made best use of the HFQ forming capability. We sketched out ideas, and Jared's team used this to develop a full-scale honeycomb concept. This was then simulated and iterated to find a geometry that met forming and application criteria. The tool has been manufactured, and we are hopeful that full-scale demonstrators will be produced this quarter. The next steps are to upgrade the blank handling for thin sheet, manufacture demonstrating parts, and analyze those formed parts. So that concludes where we are for the thin skin stiffener. Hopefully, we'll be able to show you the form panels in Aeromat 2022. So I now move on to the frame component. Here, we were at the opposite end of the spectrum in terms of thickness. Key unknowns were around the ability to form sharp corner radii in 1/60 thou or 4mm 7075 sheet, the corners having an internal R/T of 1.6. The ability to quench and develop a good microstructure are key factors, together with the accuracy of the final geometry, which directly affects the amount of post-form machining required. On the left, you can see the simulation of the forming process from blank to formed part. On the right, the temperature history during quench at 3 representative locations is shown. A fast quench is essential to ensure good mechanical properties in the formed part. A slow quench will result in coarse precipitates that reduce the final properties in the part after aging. The critical temperature range for fast quenching is approximately 400 to 250 degrees centigrade. That's the range 750 to 480 Fahrenheit. The quench rates achieved in locations in which there is excellent hard contact with the tool are simulated to reach a peak of over 400 degrees C a second or 750 Fahrenheit a second. In areas with lower tool contact, the rate is up to 150 degrees C a second or 300 Fahrenheit a second. Both these represent adequate cooling rates for achieving good final material properties. The forming tools play an important part in the tooling cost build-up, especially for low and medium run tooling up to about 100,000 parts. Here we developed and demonstrated a tooling method that enabled multiple frame sizes to be manufactured without the need to build each tool from scratch. The tools have replaceable working surfaces, shown in purple in the left figure. These can be swapped out to change between frame sizes. The tool cooling is designed to maximize energy transfer from the working surface. Large channels and thin tooling walls are used. The parts form great with no evidence of splitting. If we were to do the project again, then we would add just a little more stretch to the part in order to achieve a slightly flatter top surface. The mechanicals show we had exceeded the T76 material properties in all locations, with the results being substantially above the minimum spec of 425 megapascal yield, 500 megapascal UTS and 8% elongation. Also in this slide are the results of through-thickness hardness studies, which provide further evidence of a well-quenched microstructure. Please feel free to ask to revisit any of these slides as part of the questions. We looked for microstructure damage in the highly stretched regions. The exterior corners experience high triaxial stress states, which could have resulted in voiding in the microstructure level. The microstructure checks provided evidence of good T76 grain structure with precipitates formed at grain boundaries. The microstructure was free from triple point cracking and voiding. So to summarize the work done on the frames, we successfully simulated and formed 4mm 7075 aluminium and achieved good response to T76 temper. The original goal was to have these parts sufficiently accurate to machine from just one side. We didn't quite achieve this in the first study, and that comes down to the way the material flows into the tool. With our practical learning, we can now account for that in future projects of this type. So I now hand you back to Jared.
So to summarize these projects, for the skin application, after completion of the subscale hat stiffen features and the follow-on design, it did appear that there was a low-cost and high-rate manufacturing process possible that significantly lowered weight of traditional sheet metal fabrication at a much more affordable cost versus composite solutions. Late last year, Boeing paused efforts on the development task due to market environment. However, the skin task has been restarted this year, and we're looking forward to seeing the final results on the subscale skin bay. As for the forming of thick sheet into a complex one-piece preform, it did appear to be a significant challenge. However, the results were very promising. The overall quality of the final part is very close to what is required for a preform, and the preliminary mechanical testing showed good material properties. Nothing further has yet been restarted, but we're searching for applications in other Boeing products.
As we close, just a reminder that there are additional points of value that HFQ brings to the picture. Part integration, where we can put multiple parts into one. Down gauging, where we use less material, less costly material, we reduce more weight. No spring back compensation in the tool or the part, and in many cases, reinforcements can be removed. We would really like to meet and show you what we know about the HFQ process and how it can improve your design, save money, and reduce weight. Our contact information is shown on the right, so please give us a call. Now we will move on to a question and answer period. Thank you.